Ladies and gentlemen, please now give a warm welcome to Mr. Hanebeck.
Hello, everybody. Welcome. Yeah, I do not have such an elaborate explanation like Tian Wu about the purpose of our industry, but I would just like to put it into simple words. We love innovation. We know about the transformative role we have, and this is what we love. That's why we are all in this industry for so long. And right now, times are fascinating. It's all about AI coming at unprecedented speed and scale. And this is what I would like to talk about to you. And let's dive in a little bit. AI is coming around all corners, right? We use it in user equipment, parts. It's all over the place, and it's coming also in new forms, as I call it, incarnations, right? We have generative AI, we have agentic AI. Now we see the emergence of physical AI, which is basically AI in autonomous systems, very complex systems like cars or humanoid robots, and all that is around the corner, and I will talk about it in more detail later. But it comes with challenges, and we know there are plenty of challenges, but I would like to talk today about the power challenge. And the power challenge clearly starts with power generation, and that alone would probably fill a whole presentation, but that's not the focus for me today. For me, the focus is how to get the power from the grid all the way to the core of the processor. And that's what you see here. It starts, of course, beyond the power generation with battery systems, ESS systems, required to stabilize also the grid. If you have ever looked at load cycles of a GPU, it can be fascinating, and you see how demanding it is. But then further down, we will need solid-state transformers. We will not be able to scale the infrastructure, the power infrastructure, based on old-fashioned power transformer. It's just not scalable at the speed we need it. Of course, we need UPS systems, but we also need semiconductors for circuit breakers in order to handle these immensely high currents. And then we come into the data center itself, and that I want to elaborate a little bit more in detail. The power per rack, per IT rack, exploding. When we were talking 2 years ago about 60 kilowatt per rack, we will talk in 2 years about 500 kilowatt per rack. We remember iron is about 2 kilowatts, so 500 kilowatts, and it will not stop there. By 2030, we envision 1 megawatt per rack. And of course, it's driven by the number of GPUs, CPUs that are built into each of these racks. And the result of all that is, of course, a huge power consumption. And you know these predictions: by 2030, data centers, mainly driven by the AI loads, might use up 7% of the global energy, electricity consumption. That's as much as India takes today, but that's just a static consideration. If you think about, again, the load cycles, and if you're in Ireland, 30% of the electricity consumption in Ireland will be taken from the data center. So managing these loads becomes paramount also from a dynamic point of view. So clearly, we have to face the fact power could, not only power generation, but the power flow could become the bottleneck for unlocking the full potential of AI, and that's certainly something which is not what we want. So we can conclude there is no AI without power. What can we do? Well, Obviously, there are things which are, let's say, in the sense of improving power efficiency. We can use new power semiconductors, wide bandgap materials, improve efficiency all the way from the grid to the core, and that will help. It will help on the TCO side, right? Because once a data center is set up and running, it's all about power consumption, which is driving the bill. But that alone will not be sufficient. We need to rethink the power delivery architecture completely, because we also should keep in mind ROI. We need to build data centers which are capable to handle multiple generations of GPUs. We cannot build a data center for one generation, then there will be no ROI. So it's about TCO, it's about power efficiency, and it's about ROI, and that needs different architectures. And here we are at the forefront. Today, this is a typical rack, less than 250 kilowatts, pretty straightforward still. Of course, already demanding if you think about water cooling and all of that, but something we have learned how to handle. Now, the next step with 500 kilowatt is already a big one, where things will get separated. We will have a side rack with all the power supplies and the compute rack, and this will also then imply three-phase power supply units. But that alone only takes us until 27, so how do we handle the 1 megawatt rack? And that will be about centralizing the architecture even further. And the trick will be to get to high voltage DC delivery. So we will see 800 volt on the rack next to the GPUs in order to get the currents down as much as possible, and therefore, of course, also reduce the losses. And this is the new architecture. You see here the evolution which we have in mind from today's perspective to 27 and to 29. What is now inside such a power rack? Of course, everybody is talking about the GPUs for good reasons, but you see from a functionality point of view, in terms of power, you need backup battery units. You need, obviously, the power supplies. You need the intermittent bus conversion from 48 to 12 or to 7 volt, and then you also need the conversion from 7 volt all the way down to the core. By now, such a, let's say, Blackwell category of rack contains about $15,000 of power semiconductors. So it's a very sizable business. For example, for Infineon, it will drive about 1 billion of business next year, just in terms of power semiconductors for these AI servers. Now, this new architecture we have defined and collaborate with NVIDIA on, and we believe that will become the standard in the industry. Again, I think it makes sense to drive for a standard. We need different GPUs, but to divert on infrastructure, I think is ultimately very costly, and that's why we propagate together with other ecosystem partners this 800 volt DC delivery to the rack. Now, what are we doing in terms of innovation? Here it's quite a bit on, for example, on the PSU, but also on the IBC level. It's about wide bandgap materials. So already today you will find in our PSU solutions silicon carbide, gallium nitride, silicon, all next to each other. And we will see more of the wide bandgap material coming along that. Then we have to drive the performance of the power supply units. Currently, we have 12 kilowatts in development. Obviously, with the emergence of three-phase, this needs then different solutions. And then there is the big debate how to get the current into the processor. Some of our customers are already delivering the power from underneath, which has a huge advantage of lower resistive losses because you're simply closer to the processors. Others are are still on the lateral. We believe that ultimately only the vertical power supply, especially for the transient currents, is the solution going forward, and we have also this in our portfolio. What does it all give us? Well, it will solve the power bottleneck at least up to 1 megawatt and beyond. We need to increase power density in order to reach that by 60%, which is huge. And we need to deliver and continue to deliver best-in-class robustness and reliability. If you just think through $15,000 of power semiconductors in one rack, let's say that's about probably 25 to 30,000 pieces of power semiconductors in a rack. If you are there on the wrong side of the quality, you will see a lot of failures, you will see a lot of rework, and this I think nobody can afford. So the quality requirements of this industry are as high as automotive. Now, let me go a little bit further. As hinted already on the first page, AI doesn't stop at the data center. AI goes beyond, and we are all familiar with a generative AI. It's about generating code, text, images, whatever. We are getting into agentic AI, which can do planning and reasoning. But the next big challenge, and I took that picture, copied it from Jensen, is about physical AI. Here we are talking about very complex autonomous systems which need to manage itself in very complex environment in the sense of getting the environment in terms of perception right, understanding what's going on, and then also act in such a environment. And I would like to talk about that one as well for a while. Obviously, two examples for physical AI is the car and the humanoid robot. And let's take the second one first. What does a humanoid robot need? Well, of course, it's about main compute, but it's a lot about local computation. It's about motor control. And here, just to imagine the challenge is what we can do with our fingers. If you want to teach this a robot, you know what challenge we will face. And here, for example, also innovative semiconductor solutions, for example, with gallium nitride come into play because gallium nitride allows you to drive much higher frequencies and therefore reduce the size of the motor and the motor control. So a critical element. And of course, also a humanoid robot will require energy, charging, and lots of sensors. There are estimates that humanoid robots will contain about $1,500, at least in that ballpark. So you can imagine that this is a very attractive area, and Infineon is able to provide basically everything other than the high-performance compute processor. If you put it into a bit more functionality, then you see that, again, it's about energy supply for the robot. It's about sensors to detect the environment. It's about compute and connectivity and obviously actuators. So we are saying we need to enable the robot to sense, move, act, and connect, and all of that safe and secure. So a couple of challenges all alone in that statement. Now, talking a little bit about the car, obviously also in revolution, the whole car industry, the challenge is to bring smarter, safer and more sustainable transportation to the road. Also here, AI can help and hopefully bridge the missing gap towards autonomous, or level 5 driving. Right now, we are in the transition to software-defined vehicles. It happens as we speak, and these are the elements which are required, but more architectural changes will be required to probably achieve level 5. And one of them I want to highlight today. You're all familiar. Car is in general, if at that level of autonomy, has cameras, has radars, and the thing is, how do you integrate these data? And so far, what has been done is by camera, all data were centrally fed into the high-performance compute box and analyzed there, but for some reason, and for good reasons in the past, but no longer in the future, the radar data were processed locally and then fused in the box. Now, with higher compute power and in the central box, and also the capability to transfer more data rapidly into the box, it's safe to assume that radar and camera data will be raw data will be fused directly in the box. The big advantage out of that is that you do not lose so many points of fields by local compute, so a factor of 5 seems to be possible. That's obviously then gives you much more resolution, pushes out the LiDAR even further, so very likely camera and such a radar system can do the job. It lowers the system cost of by reduced bill of material, obviously, and also in terms of software maintenance. If you think about SOTA and so on, it becomes easier. So one of these architectural changes, and then we can apply all the AI in the central box on the raw data and hopefully close more of those corners which are still causing the trouble for level 5 driving. So to put it in a nutshell, or to conclude already, let's imagine what the future will look like. Obviously, the world will be immersed in AI power systems. We will see continuous unprecedented growth in compute capabilities if we can solve the power delivery issue. I think we hear every day the massive investments from the cloud providers. So data processing fuels all these needs in terms of compute performance, and these applications will consume terawatts of compute power. That's why the energy infrastructure will need to adjust from power generation to power transmission, all the way from grid to core, so from several 100,000 volts all the way to 0.5, and that's a business area clearly Infineon has in scope. Another area we also have in scope is Edge AI. Edge AI obviously also makes sense if you talk about latency, if you talk about specific security requirements or local energy efficiency considerations. But this, I'm sure Kurt Sievers will address in the next speech. You can count on Infineon solutions also in that space. But for today, I wanted to show you the big world of powering AI. And again, there is no AI without power. Thank you very much.
Thank you very much to Mr. Hanebeck. Thank you for your insightful sharing.